In this video, I'm going to prove that the diagonals of a parallelogram meet at right angles if and only if it is a rhombus. So let's just firstly quickly remind ourselves of what we mean by if and only if. That means that we actually need to prove this in both sort of directions, the implication. So, firstly, I'm going to prove that if the diagonals of a parallelogram are perpendicular, then it's a rhombus. So that's the implication in the first direction. Perpendicular diagonals mean rhombus. And then, secondly, that if the parallelogram is a rhombus, then its diagonals must be perpendicular. Alright, so let's start with the first direction of the implication here. And I'm going to label my parallelogram ABCD, and let's add some diagonals here. So we've got a parallelogram. We are going to start with the fact that those diagonals are perpendicular to each other, and we're going to show that that means that it must be a rhombus. So let's just note here a couple of things that we're going to use. Probably the fact that the vector AB is in fact equal to the vector DC, and also the vector BC is equal to the vector AD. So just remembering that as vectors, those are equivalent. Alright, so what we're starting with is the fact that the perpendiculars, not the perpendiculars, the diagonals, which are AC and BD, are perpendicular to each other. And immediately, if we're working with vectors, that should make a little light bulb go on in our heads, which says if two vectors are perpendicular, then their dot product is equal to 0. Alright, so let's come up with some vectors, because remember we're trying to show it's a rhombus, which means it's a parallelogram with adjacent sides equal. So in other words, if we could show that the length of AB and the length of BC are equal, then this must be a rhombus. Alright, so let's say the vector AC, if we were going to sort of go around the outside, would be equal to AB plus BC. So that's an equivalent vector sum to the vector AC. And with BD, we could go BC plus CD. So expanding that all out, what do we get? AB dot BC plus AB dot CD plus BC dot BC, dot product of BC with itself, and the final one is BC dot CD. Alright, so all of that must equal 0. So let's go through and simplify where we can. We've got AB dot BC. Now AB dot CD, well, we said that CD is, or we said DC and AB were equal, so CD is actually just AB in the opposite direction, isn't it? So CD is really equivalent to BA, which is the negative of AB. Let me just clean that up slightly. So AB. Alright, so there I've said that CD is the negative of AB. Here we've got BC, the dot product of BC with itself is just the square of its magnitude. And likewise here I can say CD is really the negative of AB. Alright, so AB dot BC, and we've got minus the magnitude of vector AB squared plus the magnitude of vector BC squared, and then minus, and we know the dot product is commutative, so I can switch this around to make it AB dot BC. So we've got AB.BC minus AB.BC, so they will cancel out. And so we're left with the negative of the square of the magnitude of AB plus the square of the magnitude of BC equals 0. So just rearranging that slightly, we could say therefore AB magnitude of that squared equals the magnitude of that squared, and that means that the magnitudes themselves must be equal. So we've found that the adjacent sides of this parallelogram are equal, and that means that therefore ABCD is a rhombus. Alright, so that was proving it the first sort of direction, the implication the first way, and then we want to prove that if this is a rhombus, then the diagonals must be perpendicular. So it's kind of going to be quite similar, but this time we're going to show that if the side lengths are equal, then the dot product of the perpendiculars has to equal 0. So here we're going to start with the fact that yes, the vectors are equal, so you know vector AB is equal to DC and so on, but also, so let's put the other one as well, so BC equals AD, but also that the magnitudes of all of the sides are equal. Okay, so this time we're starting with that knowledge, and we're going to show that therefore the diagonals are perpendicular. So let's actually take the dot product of the perpendiculars, and if we can show that the result of that is 0, then we have shown that they're perpendicular. So really just working like we were before, we'll say this is AB plus BC, dot product with BC plus CD. And so we sort of expanded all of that out before in the previous proof, didn't we? So we've got AB dot BC plus AB dot CD plus BC with itself plus BC dot CD. And now if we make some substitutions where we say that anytime we see the vector CD, it's the negative of AB. So we're going to have AB dot BC, and then substituting. So this really is very much like the previous one, and here again we can say, well, that's the negative of AB dot BC, because I've substituted negative AB for the vector CD. So then these ones here cancel again, and we've got the negative of the magnitude of AB squared plus the magnitude of BC squared. But this time, because AB and BC are adjacent sides of a rhombus, they are equal in length, as stated up in this line here. So they're equal in length, and so therefore when we take the square of the magnitude of one from the square of the magnitude of the other, it's equal to 0, and that means that therefore AB is perpendicular to CD, because we showed their dot product was equal to 0, and so therefore we've proved that if it's a rhombus, then its diagonals are perpendicular.